Hello guys, so welcome back to our lab. This is an interesting lab in which we're gonna measure the diode characteristics in two ways. In experiment one, we're gonna measure it using parameter sweep. Then in the second experiment, we're gonna measure it using the oscilloscope. This way of making a parameter sweep in a practical way. Okay, so let's start by, the first experiment in which we're gonna measure the IV characteristics of the diode using parameter sweep. So we're gonna, construct that circuit as you see here. Of course, we have something new here. We have this diode here, this guy, and these probes. And I'm gonna show you, the benefit of these probes. So let's just, omit them for a moment, just delete them, and also delete this guy here. Okay, yes, and teach you how to do that from scratch. So go to place, component, then you choose your diode. Just press D. If you are in the beginning, it will give you the start of this, list with these until you reach Mr. Diode here. Okay. Then search for our favorite 1N407G. This guy, 1N407G. You have thousands in here. Okay, we're gonna use this guy and place it here. We don't need anything else. Everything now is there. I think this is easy for you to do. So we're gonna flip this guy vertically 90 degrees, yes. Then connect it to this resistor, 1 kilo ohm, and to the ground. Okay, good. Remember, we wanna make a parameter sweep. We're gonna sweep this V input voltage, and by the way, this 3 volt, you can change it to whatever. It doesn't matter with parameter sweep. It doesn't matter the current value of V input, whether it's 0, 1000, minus 1000. It doesn't matter at all. Okay, so we just keep it. Okay, and now I'm gonna show you why we need these probes. So let's do. Remember, in our IV characteristic, which is the relation between the voltage across the diode and the current across the diode. Okay, we need a graph in which the vertical axis is the ID, the current across the diode, and the horizontal axis is the current, the voltage across the diode. Okay, with current parameter sweep here, if we go to simulate, analysis and simulation, here is a source. Basically, the input or the voltage across the diode will change based on the change in that input, and so as the current. If we go to the output, you will not find VD in here, okay? And it's ambiguous, which is which. Maybe ID1, ID is clear, that is the diode, that is the current through the diode, but which now of those V1 or V2 is voltage across the diode. So if you put a probe and you redo this parameter sweep, you will find that these probes, VD and ID, is there. Okay, so let's do it. So basically, first I'm gonna change this naming to D, just D, because we just have one diode. So it has no meaning to name it D1, which is a default naming of multisim. So just to do this, okay, now it's good. Now here is the probes. If you didn't find these shortcuts here, you go to place, probe, and you choose voltage probe. One may say the voltage across the diode is the difference between the voltage of that node, the anode, and the voltage of that node, which is the cathode, right? That's right. But remember, the cathode voltage here is 0. One may say, what if we have something in here between the cathode and the probe? Then you do the differential. So place, you have this differential, voltage, in which you can define, which is the positive terminal and the negative terminal. In our case, the positive terminal will be the anode and the negative terminal will be the cathode. In the future experiment, we're gonna check, we're gonna use it once. But just for simplicity now, we're gonna use, the similar one, which is just the voltage. So this will measure the voltage across that node in regard to the ground, which is the cathode right now, or the in the side of the diode. Now we need a probe to measure the current through this branch. So place, this is the current here, and here it is. We can also get it from here from these shortcuts. Okay. Sometimes, guys, when you place this current, this arrow here, which represents the current direction, is flipped. Maybe it's going upward, not downward like that. So to change it, basically right click and you can reverse the probe direction. So if you reverse it, it will be now the opposite to the direction of the current of the diode. So we're gonna reverse it back to that location. Now let's save first. Now if we go to the parameter sweep, okay, and check the outputs, we're gonna find by default, our I and V. Okay. Still we have here bad names as usual, so we can change also the names, make it like this. So let's just double click here on the symbol itself, and you can change here the name to VD. Okay, oops, VD. So here, yes, so VD. Okay, guys, and we can also change the, oops, I'm sorry, again, just double click on the symbol, not the name, ID. Okay, now just perfect match to this, manually. Okay, guys, now if you go to simulate, analysis and simulation, if we check the output here, it's ID and V by default. If you didn't find them, you will find them here. Just make add. So choose it from here and make add. Of course, they are chosen already and there. Before this, now we're gonna change the input or sweep the input. So we're gonna sweep 3 times here. Okay, remember, guys, the diode in the forward bias operates around 0.7. Good. In the reverse, it has a breakdown voltage. So let's check the breakdown voltage of that diode here. So to check, of course, any diode has some characteristics or parameter like VBI, like breakdown voltage, like IS, saturation current. So to check all these default values for this diode here, because remember there are many diodes made of silicon, made of germanium, different shapes, different geometry, different material. So to check that particular one, you just double click on that guy and go to yes, value. Okay, and if you want to check any of these parameters, just edit model. Here are all the parameters. For example, saturation current, IS or I node, the reverse saturation current. Here it's how much? It is 7 nanoamperes. Very small, as I said before. Okay. What else here? Let's go down. And just highlight. There are many parameters, of course, out to beyond the scope of this course. But we just very interested in some of them. Let's check. The reverse breakdown voltage or reverse breakdown knee voltage, because it's just like a knee. So they call it reverse breakdown voltage or reverse breakdown knee voltage. So it's 1000. Remember this number, it's 1000. And here is VBI. I'm going to show, the junction potential or built-in potential. It's VBI 0.7. Okay, good. Now we want to draw again. We want to draw or plot the relation between ID and VD. Okay. This relation should show us the reverse part and the forward part. In the forward part, the diode operates around 0.7, the junction voltage. But in reverse part, the current will be 0, 0, 0 until we approximately 0. It will be I naught, of course, so IS, the saturation current, until we reach the breakdown. And the breakdown happens at 1000. So to show all of this, the input voltage, the sweep voltage, this guy here, should sweep all these values. So we'll start from 1002, just beyond 1000 in the minus, to 15 volt. And the increment is 0.1. Okay. That will assure us to show the IV characteristic for the whole range, starting from the breakdown to the forward part of the operation. And in the output here again we have ID the current through the diode and VD, which is the voltage across the diode. Just now we click run. Then we export to Excel and make sure to choose both ID and VD. And wait for some time. Let's check. I think this is the one. This is a new one because I did this before. So let's now check what we have. So here you have, guys, 4 columns. You have V input, ID, then V input again, and VD. So we are interested, remember, we're interested to draw a plot between ID and VD. So we're gonna take this guy here, which is ID, and put it on the right of VD. Okay, just let's rename this. So this is VD, and this is ID, because it's our better name, of course. Then we wanna plot these together. Remember why I put the current on the right of VD? Because when you draw 2 columns in Excel, the first column will be the horizontal, the second column will be the vertical, and we want the current to be the vertical. Okay, just highlight these both, then press Shift, and then press at the same time, press Control, at the same time, press the down arrow. Then you will choose only the values that you want to draw in these 2 columns, not the whole column. Then insert and scatter here, and this guy. Wow, look guys. So we have here, here is the forward part, and here is the reverse. And you see, guys, the reverse breakdown happens around 1000. Okay, here in the forward part, it's not clear the 0.7 because 0.7 is very small compared to 1000. Okay, so now we're gonna go with this. Just screenshot or something and put this here in that. Let's close this. Put here that in that in that box here. This will show the whole IV characteristics. Okay, now we're gonna choose now, in the following parts of this experiment, we're gonna focus once on the forward part, then the reverse part. Okay, so let's continue here. After you do that, now we have the characteristics. Okay, but we can't get any something useful out of it right now because it's huge. It spans a huge range of breakdown voltages. I'm sorry, because we consider the breakdown voltage, so it spans a very long series of voltages, so we can't get something useful out of this drawing. So what we're gonna do following, we're gonna focus once on the forward part, then another on the reverse part. So let's start by the forward part. So we're gonna redo what we have done, but now we're gonna start, in the parameter suite, but now we're gonna start the parameter suite from -2, not minus 1002. So simulate analysis, we're gonna change this to 2, -2, I'm sorry. Then we click run and export again. Okay, I have the export already, so let's open what I have just to save some time. So you guys should get something like this. Okay, or in my case it's from -1, not -2. From -1, but doesn't matter a lot. From -1 until the input, let's check the input here. I think it's 15. Yes, 15. But remember, this horizontal axis is not the input, it is VD. Okay, and now clearly we can see the forward part. Look, guys, the forward part here, the operation is between 0.6 and 0.7. Look, this is how, if you put here, it's 0.679, which is around 0.68. Okay, and the current is 14 milliamperes. Okay, and we can see clearly its exponential relation, right? That's very nice. And here we can see in the reverse part that the current is almost I naught. Remember, I naught was something multiplied by 10 to the power of minus 9. It was something in nanoamperes. And as you see here, it's minus 6.2 around, or minus 6.199 nanoamperes. Okay. And we know in the reverse and the before breakdown, the current is almost equal to IS, or the reverse saturation current, which is very, very, very small. In that particular diode, it's around 1 nanoampere. Okay? Or few nanoamperes, to be more specific, few nanoamperes. Okay, now let's get something useful, insightful from the forward part. We're gonna measure the what's called the forward resistance of the diode. Okay, the forward resistance of the diode. Just like any element in our circuits, the diode has, what's called forward resistance. I mean, since you have a voltage and a current and they have some relation to each other, and there is a slope between these two, the current and the voltage, then there is a resistance. Because the definition of the resistance is a change in voltage in regard to the change of the current, or the opposite if we want to measure the, the conductance, you can say, which is 1 over R. So the mathematical definition of the resistance is it is just dV by di, or the slope, right? If it's a linear resistance, this dV by di is just the slope of the linear relation, like Ohm's law. But for the current, for the diode, it's not linear. As we know, it's exponential. But since the derivative of the exponential relation is really hard, it will give you something still changing with the voltage. So there is a more realistic way to do it. Okay. Usually in our applications, we know that for such particular applications, the current of the diode will be, for example, between, let's say, 2 milliamperes and 4 milliamperes. So we don't care about beyond 4 milliamperes or before the 2 milliamperes. And we want to know the resistance value between 2 and 4 only. Maybe in another application, your current will be between 6 and 8 milliamperes, something in here. So you don't care about currents less than 6 milliampere or more than 8 milliamperes. We just need to know the resistance, approximate value for the resistance between these two values, 6 and 8 milliamperes, 6 and 8 minutes. Of course, this is in amperes. So this is 0.006 amperes, which is just multiplied by 1000. It will give you 6 milliamperes. Okay, to convert ampere to milliampere, we multiply by 1000. Now, it's interesting if we look here, this is approximately linear, right? This is approximately linear. So we can approximate the relation between, for some regions, for the IV characteristic as a linear. Okay, and that's what we're gonna do now. We're gonna measure the resistance between 6 and 8 and 2 and 4. So let's do that. I already did it, but I'm gonna show you again. So for example, let's see where I have done it. Okay, it's on another sheet, but that's fine. Yeah, so let's get the other sheet better. Yes, this guy. Okay, so for example, between 6 and 8 milliamperes, between that point and that point, it should be here. Yeah. So look, guys. So what you're gonna do? Let's do it from the beginning. That's better. So we just write equal in any cell in the Excel sheet. Write equal. So now Excel is ready to receive from you a kind of calculations that you want to do. Okay, good. So what we're gonna need is the slope between these 2 points. So the slope is, remember, we're gonna measure a resistance. So volt minus volt, we're gonna approximate it as linear. So we need the slope. The slope is y minus y over x minus x. But remember, we want to measure the resistance. So the resistance should be voltage minus voltage over current minus current. If we, approximate the relation as linear. So we're gonna measure the current at 6, voltage at 6, milliamperes, and then the voltage at 8 milliamperes, or the opposite, if you wanna, of course, the voltage at 8 is higher. So the voltage at 8 minus the voltage at 6 divided by the current here, which is 8 minus 6 milliamperes. Good. So just look at the data that you have here. Okay. So just open a bracket here. We want the voltage when the current equal to 8 milliamperes. So just look at the numbers. So here is 0.0079 and here is 0.008. So consider this approximately 8 milliamperes. Okay. But remember, we want to measure here is the voltage. Here is the voltage at current equal to 8 milliampere minus. Now we want to know the voltage at 6 milliamperes. So we're gonna go up here until, yeah. Look, guys, here is the current is 0.0059. Here is 0.006. So we can consider this is a 6 approximately. And here is the voltage at 6. Okay, so this is, you know, voltage minus voltage. Now the current minus current. So you're gonna divide this over the current at 8 milli, which is 8 milliamperes, of course, minus 6 milliamperes. So now, what is this relation is? This is the voltage at that point, minus the voltage at that point, divided by the current at that point, which is 8, minus the current at that point, which is 6. So this is dV over dR. So this will give you the resistance. So let's just hit enter. Wow. So the resistance of the diode in that region here, approximately, remember, this is we approximated the relation as linear, is 0.6, 0.7 ohms. Let's write this ohms. Okay. Before we go forward, it's very small. It's extremely small. So you know, guys, that, you know, some insight here is that whenever the diode start to conduct, usually beyond 0.7, look here, this is beyond 0.6, around 0.7. Usually the resistance of the diode is very small. Okay? And as we go forward, the resistance will decrease more and more. Good. To prove that if we go forward, I mean, if the diode voltage increases, the resistance decreases. Okay, we're gonna measure the resistance now, but between 2 and 4. If we look at between 2 and 4, looks like the slope here, if we approximate again the relation to linear, the slope will be lower than the slope between 6 and 8. This is more steep. This guy between 6 and 8 is more steep, more to the vertical than this guy. So we are expecting here to have less slope, which means higher resistance. So if we do it, I already did it for you, it's 16 ohms. So the resistance of the diode approximately equal to 16 between 2 and 4, and approximately equal to 6 between 6 and 8. That means if we increase the voltage across the diode, its equivalent resistance, we can say, decreases. And here is the approximate, here is a proof, experimental proof for it. We measure the resistance between 6 and 8 with high current or higher voltage, higher VD, and it was less than the resistance for lower voltage or lower ID. Okay, guys, but for our manual, because now you have the values, so I will ask you to calculate the resistance for other points. So let's check the manual. So the manual here is asking you to get the resistance between 1 milliampere and 2 milliamperes. So let's go back here. Between 1 milli should be the halfway here, and 2 milliamperes. Then between 12 and 14 milliamperes. So yeah, because this is just at, if we sweep to 15, this guy will go to higher currents between 12 and 14 milliamperes. If we go back to this one here, Look, guys, 14 million, 12 and 14 milliamperes. Okay. Okay. So what else we need here? So let's. This is for the forward part. Now let's focus on the reverse part. In the reverse part, we need to measure the breakdown voltage. The breakdown voltage. Okay. So we're gonna measure we're gonna now sweep the input, V input, between minus 1002 to minus 980. Okay. So just bring this down. We don't need it now. So we're gonna go to simulate again. Analysis and simulation. Now the input between 1002 to minus 980, and just the output is still the same. They didn't change ID and VD. And click run. Export it to Excel. Choose all. Okay, my friend. Then we wait a little. Maybe it does it. Yeah, it was very fast. Oops. Yeah. It's fast because Excel is already opened. That's why. Again, you have 4 columns: V input versus ID, V input versus VD, but we need VD versus ID. So just to change the names again to make it very clear for you. And this ID here. Again, shift, control at the same time, down arrow at the same time, go up, and insert this guy. One may say, where is the forward button? Because we swept only for the minus between, so we will not show the forward button. And here is, our interesting area here. Okay, this one. So if we increase this more here, we want just to measure the knee breakdown voltage, and you guys can, approximately here, if we go this point, maybe just hover over this point, it's around, it's around 1000. So if I cannot, maybe it's so look, guys, this point. So the next point, you will have a current, higher current. Look, second point, third point, fourth. So this may be this one. I am not sure if it's clear for you. Yeah, we can zoom in. Yeah. So we interested in this point, this one. Okay. So look, it's minus 1000, minus 1000.097. Okay. So this is basically our breakdown voltage. Okay. And one may say, but we know it already. Yes, we know it because we double clicked on the model and we knew it we cheated. But if you want to know the breakdown voltage using experiment, you should do something like this. Okay. Also, it's very hard because we cannot have a source that can give us in a lab, in a small lab. You cannot have a source that can give you 1000 voltage. It's really hard. Okay. So you guys bring this value and go back to the manual here, put this relation in that box, and put here the voltage. Okay. And before I forgot, if we go back, we now finished the experiment 1, but there is some points that I forgot to mention, or I mentioned indirectly, that when you measure the resistance between 1 and 2 and the resistance between 12 and 14, for sure, you will find that the resistance between 1 and 2 is higher than the resistance between 12 and 14. And I said the reason. It's exponential relation. The change in I increases as we increase the voltage VD. That's why the slope become more steep when you increase the voltage VD. So that's why you have less resistance. Okay, so you just write this reason here, why the resistance between 12 milli and 14 milliampere is lower, much lower than the resistance between 1 milliampere and 2 milliamperes. Okay, guys, that's the first experiment. Just stay tuned for the second video for the second experiment. Thank you very much and goodbye.